two speakers, Takumi Nomura and JASPAR. And it's speaking on guidelines for using IEEE PCR and JASPAR PPA connector, Nomura Qbv Dominant. So please welcome Takumi and Yoshihiro.
Hello everyone. My name is Takumi Nomura, Vice Chair of the JASPAR International Transport Network Automotive, and I'm also a chief engineer. And this is Osa, Professor Goto of Nagoya Institute. Today, we would like to talk about guidelines for using IEEE in JASPAR's B2 network. Why IEEE and B2 As you know, software-defined B2 SDB is now attracting attention these days. SDB is expected to realize new constraint user experiences by consolidating B2 functions to central ECU. So what exactly is SDB? Thus, consolidating functions into central issue mechanism SDB. That means that simply consolidating functions to central is not enough to discuss the definition of SDB. Zonal architectures and networks are also key to realize SDB. So this presentation discusses the state of networks in SDB. Here is the gem for this presentation. Shifting to SDB, how will in-B2 communications change? And next, we discuss three TSM shaping mechanism. And finally, we evaluated the shaping technology, so we will report the result. It is said that the mobility industry is facing a once-in-a-century innovation. Mobility as a service shift. There are a lot of keywords, but for network engineers like us, the most impactful brand is SDB, right? In fact, the Japanese industry organization JASPAR recognizes SDB as a top priority. The computing thing about SDB is its broad scope. SDB is not just a machine, but an ecosystem called SDB. The data created in B2 is sent to cloud via OPA. And the data will be analyzed and fed back to software development. Newly developed software components will be installed to B2 by OTA, and brand new data will be created in the B2. So, as you know, completely different data flows from the conventional ones. This presentation focuses on integral networks. Now, let's discuss the innovation in integral networks to realize SDV. As you know, E&IP architectures is evolving from the conventional one to the domain architecture and then to the central zone architecture. Legal functions will become software components and centralized to the central ECU, so-called SDV. But we think simply consolidating functions is not enough to develop SDV. Zoning and device containment is also important. Central and zone are two sides of the same coin. Okay. Let's discuss why zone is important. This is a diagram of conventional architecture and central zone architecture. In the conventional architecture, the network carries multiple commands and responses in the network. What happens? We employ the central and zone architecture. As I mentioned before, functions are integrated to the central ECU and devices are revealed. So, in the channel, the zone between zone ECU and devices, this channel includes the raw data of devices. And between central ECU and zone ECU, the raw data is transmitted over Ethernet. In other words, the central zone architecture will significantly change the data transmission through channels. Therefore, central zone architecture will have different requirements than before. The first requirement is responsibility. Initially, in the conventional architecture, it was wiring inside that ECU. So, delay should have been virtually zero. This data will flow between central ECU and devices via zone ECU. While it is challenging to make the latency virtually zero, it must be shortened to the acceptable level according to the system requirements. The second requirement is reliability. Originally, data losses should have been virtually zero. Thus, zero frame loss reliability will be required. Let's discuss the behavior of the network between device, zone, and central. Now, let's look at the print. The information from devices will be interpreted by zone. The Internet frame is transmitted to central ECU. Depending on the number of devices and zone gateways processing performance, increasing of the boundaries between zone and central can accommodate the law. Therefore, this seems to be no problem in the trade. The problem lies with the downlink. The surplus capacity in the link is a risk for the downlink. If the central ECU output too much frames at once, it can exceed the zone's processing capacity. Therefore, to prevent the overflow in the zone, the selection and design of two-way protocol are crucial. And now, let's consider which protocols are appropriate from an OEM perspective. This figure shows the output code from the central ECU downstream. There are queues according to the priority, and data are outputted based on the priority. This is simplest method is strict priority as defined in IEEE and O2. With strict priority, high priority frames are always sent first. A strict priority is easy to understand and highly effective, so we think it can be used for many use cases. However, in case of the central ECU, prioritizing only high priority data can result in fast overcrowding. Fast traffic that can cause flooding in the zone. This is an extreme example to make the discussion easier to understand. In that, if the input traffic is not fast, even if the high priority and low priority data are mixed, that QoS functions in the switch will not be triggered. And then there seems to be no problem with the output traffic. On the other hand, if the original traffic is busted, simply using priority is not sufficient. After high priority data is sent, the low priority data will follow. As a result, the burst will burst. Therefore, a method of avoiding burst, such as shaping, is necessary. Fortunately, Ethernet DSL has several shaping functions. This situation is both fortunate and unfortunate for OEM. The reason is that we can use shaping technology effectively. The benefits is very significant. However, it is challenging for OEM to use them effectively. and balancing the difficulty and the effectiveness is also different. I want to make this situation easier to understand. First, let's look at the critical shaper. CBS is very popular and widely used, so no explanation needed. It's relatively easy to implement. And implementation is not required. Additionally, although not mentioned here, almost all automotive design switch have CBS function. Therefore, it is best to start with CBS. Another well-known shaper is Nagoya shaper. It is similar to television multiple access. This could be realized. Data transmission would be possible, but designing the schedule would be extremely difficult. As I mentioned before, the balancing difficulty and benefit is crucial. When it comes to us, difficulty seems to outweigh the benefit. CBS Express shaper is excellent, but relying solely on its own CBS is not good for years. And therefore, we need other options. So we focused on synchronous traffic shaper. Unlike this shaper, it can control the maximum latency. This is a good point. The implementation of ABS is less complicated than PAS and allows for more precise control than CBS. The balance between difficulty and benefit is good. ABS can be a promising option to complement this shaper. So far, we have compared the three PSN shapers from an OEM perspective. It has its own pros and cons. But key point is the balance between difficulty and benefit. From this perspective, critical shaper and synchronous traffic shaper are good technologies. To clarify the effectiveness of critical shaper and synchronous traffic shaper, we have quantitatively evaluated them by traffic simulation. Professor Ito, my co-author, will explain this in more detail. Professor, please go ahead.
My name is Yoshihiro. So I'd like to demonstrate the Nomura-san explained this part using some technical results. And we conducted very simple simulation and to help you better understand our argument. And this figure shows model. In this model, shows the use case of in this case, Nomura-san explained earlier. And in this model, the central SOC functionally integrated to 7 zones. And the switch connect to central SOC to 7 zones. And since it was refrains from the central SOC to corresponding zone according to the range value. And this switch supports both ATS and CBS. And the ATS and CBS are applied between the output interfaces. And each issue receives mapping of corresponding priority. And the mean and variance of the generated quantity. The mean and variance of the transmission rate of the integrated quantity changes by priority. But I would like to notice that priority 4 is omitted in this experiment because in many cases the priority 4 quantity we use preemption. But in order to simplify our discussion, we omit the use of preemption. So the line speed between central SOC and switch is 1 megabit per second, and the line speed between switch and each zone is 100 megabit per second. So let's discuss our results. This figure shows our results. The left figure shows the maximum delay, and the right figure shows the level of rate. And this figure indicates the result for priority. And we use either ATS or CBS on the switch. And of course, from the left figure, we confirm that ATS can suppress the maximum delay more than CBS by setting complete bus rate size, which is the one of the English parameter. And the maximum delay can be managed by adjusting the complete bus size. On the other hand, the right side, the right figure shows from the right figure, we can see while it is suppressing the maximum delay claims that it is the maximum resistance time at this time. So, it is the more process than series. From this result, so we see that it is allows the choice of appropriate point in the trade-off between the maximum delay and plane loss rate. So next, I'd like to show another result. And this figure shows the result using the quantity is the lower mean saving rate but more extensive variation than the previous one. And similar to the previous slide, the left side means the maximum delay, and the right figure means the level rate. And from the left slide, the maximum delay can be suppressed entirely in ATS because frames are no longer held in the total bucket due to bursts. On the other hand, the right slide shows the ATS, while ATS suppresses the maximum delay, frame loss occurs in ATS, even though there was no frame loss in GBS. From these results, we have two conclusions. First, data with a time, data with a time structure, the basic data that becomes meaningless after the explanation time. For example, so overfitting and development and so on. Such data should be transmitted by ATS, and ATS can manage the expiration time. The second, CDS should be used for data that is more sensitive to missing data than time constraints. CDS is right, is very easier to implement than ATS. So we'd like to show JASPAR's guideline of automotive network design from the obtained insights. Firstly, the main structure is constructed based on CDS because CDS is very easy to implement and configure. And the second, it is better to apply ATS to time-sensitive data selectively. And these two issues show, from these two issues, we want to say the right person must be in the right places. But in order to adapt both ATS and CDS, we must optimize the parameter to trade-off responsiveness and reliability. So in general, it is not easy to obtain the optimal value to adopt both ATS and CDS over actual environment. So it is better to use simulation to obtain such optimal values. And then we should implement such values. And finally, we conclude. So we conclude. For individual method, it assumes that CDS and tasks will be adapted, but they may be only sometimes optimized. However, in many cases, we use only CDS ATS. I think the reason is a near conventional one. So now we know that the conventional reason is meaningless. Therefore, we should also take the combination of ATS, which has more control variables than CDS. And finally, we conclude our presentation. So please, please.
Thank you, Professor Tom. Let's summarize. This study analyzed the effect of communication caused by the centralization of functions in central ECU due to the action of SDB. It clarified that SDB network requires responsiveness and reliability. This simulation clarified that shaping is necessary to avoid bursty traffic to achieve both responsibility and reliability. Two shaping standards of IEEE SA were qualitatively varied, and their related characteristics were tried. In particular, this study focused on CDS versus ATS and evaluated the effect quantitatively and relatively. Thank you for the attention.
thank you. Does anybody have any questions? We have a couple more minutes. Oh, okay. Actually, I'm here. So you first, you second, you third. And then we'll close the you.
Okay. Yeah, thank you. I have a question on the case that is shown on slide 21. Yeah. So it's really the underlying use case on the right-hand side. You get this framing basically by setting maximum residence time quite low. And if you bump it up, you avoid the frame loss, the delay goes up. Is the underlying use case in the way that framing is acceptable, or because otherwise we would set it differently, I would assume. So this frame also in this case is acceptable as a position.
So this kind of question. I think the hours of that was late is not qualified because I think the OEM must clarify that use OEM must show the use cases and we must define the tolerance for brand losses. But I don't know the deadline of brand losses. But however, I think you, as you said, we can change we can control the brand loss rate. So by controlling the bus size or market size. So in this case, we only show the tunability of the APS. So this figure, therefore this figure does not show does not show the appropriate brand loss rate value.
I was just wondering about recovery after you hit your 100% failure rate. Is there any significant time difference between ATS and CBS? So I would assume that when you hit 100% train loss, there's some time associated with recovery. Is there any testing that you did that showed one was better than the other?
This is the only one result. So if we change the environment or specification of target and the proportion and so on, so we can get many kinds of results. So I cannot say the general conclusions. So as I said, we want to say the tunability of APS and I think so this value has not so important users.
Hello, I have a question regarding your delays that you measured. How did you define what you were measuring? Was it the moment that the frame started making the switch, ingressing and egress? And then what tools did you use to measure that latency?
So how do you use it? You mean so how do we measure the latency? So this experiment was done by simulation. So it is easy to calculate the latency.
Okay, that's very good. Thank you.
Great, I'll listen to you on that one, staying on track. Thank you very much.